Okay, this video is to go over investigation 1D invariant. So throughout this lesson, we were looking for invariants so that we can pull out some meaningful items from our experiments. So the first thing we want to go over, the term we want to go over is collinear points. Collinear points tells us that if you have some points, 2, 3, or 4 points that is on the line, that is on the line, we say collinears. These 3 points A, B, C are collinear. And concurrent line means, let's say we have 3 or more lines that meet at 1 point. We say these 3 lines are concurrent. It could be 4 lines, it could be 5 lines, as we see in the class. Constant means numerical invariant. So we only can use that for numbers. So for example, the length AB and length BC are constant because length is, we can express that in numbers. But we don't say that the shapes inside the triangle or the shape is constant, shapes are constant. We don't say that. We say shapes are invariant because constant means numerical invariant, not the spatial invariance. This is the circle that you cut out, and we did that experiment in lesson 1.12. That's the disk, just like compact disk. Invariance, that's the items that doesn't change. And we went over in this investigation 3 important conjectures and theorem. And first, midline conjectures. That is midline conjecture is that midline conjecture is it says a segment connecting the midpoints of 2 sides of a triangle is parallel to the 3rd side and it's half of its length. So if you have any triangle like this, if you take midpoints, if you connect that line is parallel to the other one, and also the length from the parallel line inside the triangle and the base will be a half of it. So the length from here to here is half of here to here. Any triangle that is true, even obtuse one, take the midpoints, connect it, that's parallel to these 2, and the length from here to here is exactly the half of here to here. And we saw that on experiments. The next theorem we went through was that concurrence of perpendicular bisector. So if you have, that's theorem 1.2. If we have triangle, let's say we have perpendicular bisector, so take a midpoint and perpendicular line, take a midpoint and perpendicular line, take a midpoint and perpendicular line. Those gonna meet at 1 point. Those 3 bisectors are concurrent all the time. Here's the reason. Because this point right there is equidistant from, let's say, triangle ABC, and let's say the concurrent point is P. The length from PB is exactly the same as AP because it's perpendicular bisector, and by theorem 1.1, the length from PB is the same as length from AB because this point is on the perpendicular bisector of AB. And also, lengths from AP to AC is exactly the same because that P is on perpendicular bisector of AC. And because of transitive property, if BP is the same as AP and AP is the same as CP, therefore CP is the same as BP, as you see, right? Then if BP is the same as PC, the converse of theorem 1.1, that point has to be on the perpendicular line. Therefore, that point is on 3 segments, 3 perpendicular bisector. And theorem 1.3 is angle bisector theorem. So if you take any triangle, if you bisect the angle, roughly speaking, and that's going to be concurrent right there. Because if you take, let's say, ABC, let's say DE, triangle DEF, and the midpoint is M, not midpoint, concurrence point is M, then the distance from, because those are bisecting angles, the distance from M to DE, distance from point M to DE is exactly the same as distance from M to DF. Okay? Because it's bisecting the angles, right? Although it doesn't look like it because of my poor sketch. And that also tells us that the distance from, if you look at these 2 angles right there and right there, then that means that the distance from here to EF to the midpoint M will be exactly the same as distance from point to DE. Therefore, the distance from all 3 sides to the point M are exactly the same. Therefore, that line meets at one point. And that's about investigation 1D.